diffusion of gases out of our bloodstream or into our bloodstream. Last week was chapter 4 on ventilation. This is on gas diffusion. We will do chapter 8 next week. The week after, we will be testing. So this test still is a couple weeks away. We'll have a test tomorrow, obviously, in patient assessment, but fundamentals, we'll have a test before we test in here. So just kind of keeping track of the upcoming test. The chapter itself, as far as length, is not exceptionally long, but there are some very important parts of the chapter that we need definitely to discuss, because it's very important for us to understand and know this. So diffusion, simple diffusion. Movement of molecules from areas of high concentration into areas of low concentration. When we talk about diffusion in the lung, we're talking about diffusion of two gases in particular. What two gases are these? Oxygen and carbon dioxide. So those are the two primary gases we're talking about when it comes to diffusion. Diffusion will occur between the alveolus and the capillary. That's, again, leading to gas diffusion going from the alveoli into the blood or from the blood into the alveoli. So that's one location where gas diffusion will occur. Another location for gas diffusion to occur is between the blood and then the tissues, where we're delivering oxygen to the tissues and removing carbon dioxide from the tissues back into the bloodstream to be carried back to the lung. We'll go over it, and I don't care if I have to repeat myself umpteen different times. It's important for us to understand those two gases, oxygen and carbon dioxide, as they make their path throughout the body. So gases will diffuse, again, like I said, from areas of high concentration to low concentration, but specifically, it's based on their partial pressure. So partial pressure does mean the concentration or the number of that particular gas. And we'll get to some numbers today and be able to recognize that, yes, the gas is going to go from where the number is higher to where the number is lower. Eventually, until they reach an equilibrium. But if one location is higher than another, then gases will move from wherever the pressure is higher to where the pressure is lower, again, until an equilibrium is met. And it's due to those differences in the partial pressures. All right, so gas diffusion. Each gas in the mixture, in this mixture specifically, oxygen and carbon dioxide, has its own diffusion gradient going from high pressure to low pressure. And we're, again, my example here, here's the alveolus, here's the blood, here's the capillary. That area between the two we refer to as the alveolar capillary membrane that gases are going to diffuse through. Now, oxygen we know will diffuse into the bloodstream, and we know carbon dioxide will move from the bloodstream into the alveolus for us to exhale that carbon dioxide. And we know this continues every time we're breathing. The neat thing, or nice thing, I guess, about these gases diffusing is it can all happen at the same time. As oxygen is moving in, carbon dioxide is moving out. It can all happen simultaneously based on each gas's own partial pressure and that partial pressure gradient between those two gases. The next several slides, 4 or 5 slides, did not come from the textbook, but I like the way these pictures kind of give an example of how the partial pressures are represented as those gases move throughout our body. So like I said, you're not going to find these next several slides or pictures of these next several slides in your textbook. They're part of my PowerPoint here. So again, just to get a picture of what we're looking at. Here's the alveolus. Here's the bloodstream, so the red blood cell. We know that location between them is the alveolar capillary membrane, and we know gases are going to diffuse from where to where? High concentrations or high partial pressures to lower concentrations or lower partial pressures, because there's a gradient there. So let's start in the lung. You just took a breath in. There's now oxygen there in your lung. The oxygen concentration is going to be higher in your lung, or the alveolus, I should say, than your bloodstream. Okay? That oxygen goes into your bloodstream. At that same time, carbon dioxide level is higher in your bloodstream than it is in your alveolus. And so where's the carbon dioxide going to go? Leaving the bloodstream and going into the alveolus for us to be able to exhale for the very next breath. Okay? That's where we're going to start.
So it's a supply, exchange,
and it's really, I like that, it's an exchange. Okay? We know our tissues need oxygen to perform. We know when our tissues perform, the waste product carbon dioxide is going to be produced, and our body obviously has to get rid of that waste product. So it is this exchange of these gases. But again, they're occurring separately from the other, right? Now picture it. We have the oxygen. It's in our bloodstream now. Now, that blood is going to go back to our heart, where our heart then is going to need to pump that good oxygenated blood to the rest of our body, or to the tissues that need it. Needs that oxygen. Okay, so the heart's going to pump that oxygenated blood to the tissues where the tissues really need that oxygen. Once the bloodstream reaches that tissue level, the oxygen concentration now is higher in the bloodstream than it is in the tissue. Okay, careful, make sure you do pay attention to what we're looking at here. This is not an alveolus anymore, this is the tissues. This is my right leg because I'm about to move it, or my right arm because I'm about to move it. That's the tissue we're talking about. That muscle or that tissue that needs to move. All right? Oxygen concentration is higher in the bloodstream than it is in the tissue. And again, we have gas diffusion. Now the tissue that was using the energy to perform and create the waste product carbon dioxide, that carbon dioxide level is higher in the tissue than it is in the bloodstream. So where's that CO2 going to diffuse to? Out of the tissue and into the bloodstream. Everybody okay so far? And again, we can do this over and over again. It's okay. Now that we've extracted, the tissues have extracted the oxygen that it needed and provided the blood with the carbon dioxide that it was getting rid of, that blood then has to go back where? Back to the heart, for the heart to now pump that blood into the lungs, where it's now going to get rid of that carbon dioxide, because the carbon dioxide in this point is higher in the bloodstream than it is in the alveolus. There goes the carbon dioxide. But guess what? It was deficient in oxygen because the body, the tissues used the oxygen it needed, so the oxygen is higher in the alveolus. Oxygen goes back in the bloodstream. And this whole process starts all over again. So this is really the opening slide we did, okay, to show that passage. So in the beginning, oxygen levels are higher in the alveolus than they are in the bloodstream. That's what causes the oxygen to go into the bloodstream. Carbon dioxide levels are higher in the bloodstream than they are in the alveolus. That's where the carbon dioxide leaves the bloodstream and goes into the alveolus again for us to exhale it. And the process continues and repeats. Okay? Wherever the concentration of the gas is the highest, it's going to leave that area and go to where it's the lowest. Until what happens? They equal. They reach an equilibrium. And then diffusion stops. Questions? Right, yeah, there's never a pause or never a halt or anything like that. I know when I say it, it's like, okay, let's all go ride the train.
Hold on.
Okay, everybody get off and on, that we need, and then on to the next. Yeah, this is constantly happening. Second by second, it's happening. Again, because your heart's, while you've been sitting here, your heart never stopped beating, right? Just making sure. I think I would recognize if somebody's did, but it never stopped.
If it did, you better call the hospital.
So it's continually beating, blood's continually moving, even though I'm not necessarily breathing as frequently as my heart's beating. I'm breathing enough to make sure the oxygen is in my alveolus. It needs to be there, and as the blood goes by, it's picking up what it needs, and it's taking whatever carbon dioxide that is necessary that it needs. Everybody okay? Yeah, we can go back when it's all said and done and repeat this whole part again. All right. So the respiratory exchange ratio, abbreviated R. Okay. Respiratory exchange ratio. This represents the ratio of carbon dioxide diffusion into the alveoli compared to oxygen diffusion out of the alveoli. I wish I could say it was a 1-to-1 ratio, or it was a 1-to-1 relationship, but I guess that would be too easy. So it's not an exact match, right? As far as the amount of oxygen going in versus carbon dioxide coming back out, or vice versa. It's not a 1-to-1 match. So at rest, now these numbers will change if we are exercising or exerting ourselves. So simply put, at rest, the pulmonary capillary, the blood, removes about 250 mLs of oxygen per minute from the alveoli. But CO2, only 200 mLs of CO2 diffuses from the blood into the alveoli. Okay, so it's not the same number going in, going back out. Again, remember, there's two separate gases. As far as what's coming out of the alveolus into the bloodstream, 250 mLs of oxygen. I put it in bold because the number is probably important to remember in some form or fashion down the road. But as far as how much CO2 gets moved or brought in, only 200.
So
it's not an even match. I'm sorry.
So as they create the exchange and remove and then redistribute, is it because of their concentration is different?
Again, their concentrations don't apply to each other.
Okay.
Okay. Then their numbers are going to be different. The partial pressures are going to be different for oxygen and carbon dioxide, but their exchange is not even. You know,
Okay.
for 1 ml of oxygen exchanges 1 ml of CO2. Then not so much. Not so much. It's not an even match. So you may hear the term oxygen consumption. How much oxygen are we consuming? 250 mLs of oxygen. Versus how much CO2 is being produced? Only 200 mLs of CO2 is being produced. Now you know me already, and you know my tricks on the test. When I say which of the following represents oxygen consumption, now we know what the right answer is, right? 250, but do you think 200 is going to be an answer option I'm going to give? Of course I am, right? Of course I am. So it's easy to get them confused. I know I've seen some students before, because I may ask both questions on a test, right? Oxygen consumption, CO2 production, ask them both. I've seen students answer the exact same answer for both questions. I'm like, well, you know it can't be the same. They're like, yeah, I was getting them mixed up, and I at least wanted to make sure I got one of them correct. I said, oh, you're not a very strong gambler, are you? And I would have rolled the dice, and I would have went one versus the other and hope I got them right. But they didn't want to get both of them potentially wrong, so it was a 50-50 shot. Okay?
It's like the difference
I can relate.
the amount due to stuff like the dead space, or just for the...
Nope, that's just what it is. It's just what it is.
Is it always gonna be 50? Like the difference? Yeah.
For
I
the
mean,
most part, and again, I'm emphasizing at rest.
Okay.
At rest. Numbers are obviously going to change if we're exerting ourselves, and again,
Right.
depending, we're both racing, but I'm running at 50% effort, sorry, use 50, half the effort, you're going full speed. Of course, how much we're taking in, moving is going to be different.
Right.
You know, just depending on how much we're exerting ourselves. So, if CO2 production's around, and again, it's an around number, but it's okay, because you got to remember something. It's around 200 mLs, and oxygen consumption's around 250 mLs. That means the respiratory exchange ratio is about 0.8. Remember I said this is not a 1-to-1 relationship, so respiratory exchange ratio is not 1, it's 0.8. Again, it's the ratio of CO2 production divided by oxygen consumption. Normally around 0.8. Which means the amount of CO2 entering the alveoli is about 80% of the amount of oxygen leaving the alveoli. Again, 0.8. Totally confused now? So just wait. Wait till you see this picture. Zoom in on that camera. Not kidding. This, I wrote it down, I don't remember. Page 127 of the textbook is this picture. Alright? So bear with me as we talk about it. Okay, bear with me as we talk about it. Think about diffusion gradients. Alright, diffusion gradients, high concentration to low concentration. That we know. We walk out here knowing nothing else today. Well, no, diffusion means going from high concentration to low concentration, right? So, let's start about here. Now, let me step back. The heart, this kind of matches those drawings I gave you earlier, minus all the numbers that can get very confusing. So, here's the heart. What do you think this red blood represents? Oxygenated, and the blue blood represents deoxygenated. Okay, so if we start here, inside the alveolus, the partial pressure of oxygen is about 100 millimeters of mercury. The CO2 is about 40 millimeters of mercury in the alveolus. Now, if you think about, again, diffusion, high concentration to low concentration, on that deoxygenated side, the amount of oxygen is around 40 millimeters of mercury. Again, inside the alveolus, it's 100. So where is that oxygen going to want to flow? Into the bloodstream. CO2 levels, about 45 on that deoxygenated side, about 45, but in the alveolus it's 40. So where's CO2 going to want to go? Again, to where the lower number is, until what happens? Equilibrium. Okay, so now we've taken this, we've reached equilibrium. So our arterial system, arterial side, the PO2 is about 100 millimeters of mercury. CO2 is about 40 millimeters of mercury. This is what's going to go back to the heart, and then the heart pumping that to the tissues that need them. Now, just to explain a little bit, by the time that blood reaches the heart, it's not exactly 100. I would say, if this was my picture that I could create, I would right now just leave it at 100 for simplicity's sake. It's not quite 100. There is, and we'll get to it in time, there is some mixing of some venous blood with oxygenated blood. It's what pulls this down and why it's not technically 100. But for right now, I think it would be okay just to simply say, for simplicity's sake, let's call it 100. That gets into the heart. Heart pumps that arterial blood to the tissues. And so let's take it down. So here's the tissues that need the oxygen, and we're going to give up some CO2. If the PO2, and we'll just use what's the number in the graph here, is 95, as far as O2 in the tissues, it's much less. And that's why oxygen will diffuse into the tissues, because the amount in the tissues is much less than the 100 or 95. Carbon dioxide levels are much higher in the tissues than they are in the arterial blood, and so they will diffuse out. Now, I will point out a couple of things about this graph, and been in multiple editions of this picture. Drives me crazy. They have it labeled wrong. I wish I could just eliminate this tissue part and just write the word tissues down here and say, you don't need to worry about the numbers, and really you don't. But anybody notice oxygen? Oxygen? That should be CO2. That should be CO2. So if you wanted to fix it on your picture, that's fine. If anything, I don't want to get too much into the levels in the tissues now, but just recognize the oxygen level in the tissues is lower than it is in arterial blood, and the CO2 levels in the tissues are higher than it is in arterial blood. And so obviously things will go until what happens? Equilibrium. And so now on the venous side, remember the body, and why do we call it deoxygenated blood? Because the body extracted the oxygen that it needed. The tissues extracted the oxygen that it needed. But did you notice something? It doesn't take all of the oxygen. So the oxygen level on the venous side isn't 0. It's 40. Definitely not as high as it was originally on the arterial side, but it is 40. So if I follow up this with, well, what do you think the saturation of deoxygenated blood is? It's not 0. The body doesn't take every ounce of oxygen out of the bloodstream. It takes a good amount, but it doesn't take everything. CO2 levels that were 40 on the arterial side are now around 46 on the venous side. Not a huge difference like it was on the oxygen side. Now this venous blood, going back to the heart, going back to the lung, again, for gas exchange. So now that the levels of CO2 are higher in the bloodstream than they are in the alveolus, CO2 diffuses out of the bloodstream, the venous blood into the alveolus, and oxygen that the body extracted what it needed. Now the oxygen level is lower in the venous blood than it is in the alveolus. Gas will diffuse, and the whole process starts all over again. Sorry for the graph or picture to be so much, because I know looking at it, and especially initially, you're like, what the hell is all that? It can be very confusing. I've added a second, well actually I'll get to the second picture in just a moment, but as far as numbers, I want you guys to remember. Numbers that I need you to remember. The normal partial pressure of oxygen in the alveoli, normally, and this is breathing like you and I are, room air, normally it's around 100, that's millimeters of mercury. By the time the body's extracted the oxygen that it needed, on the venous side, partial pressure of oxygen is around 40 millimeters of mercury. CO2 in the alveolus is around 40, but by the time it's gone through the circulation and the body's added, because it's trying to eliminate the CO2 that the tissues produced, by the time it's over on that venous side, normal venous partial pressure of CO2 on the venous side is around 46 millimeters of mercury. And it should be worth noting that the difference between arterial and venous oxygen is about 60, where the difference between arterial and venous, or alveolar and venous CO2 is only about 6. Totally confused? 100% confused? Good. Welcome to respiratory care. I'm here all week. And that's where this graph, again, I wish I could create this just to make the numbers a little bit more simplistic. It's generally on that venous side around 46, 45, 46 if I had to give you a range. But just to pick a hard and fast number, we'll call the venous CO2 levels about 46. Now, in this next picture, I like this picture, not from your textbook, but I like this picture because it gives a very simplistic example of that. Okay, this previous graph, the graph that's in your textbook, I actually like this one because it's a very simplistic version of the same thing. But it's looking at each gas separately. So here's oxygen. And the alveolus, it's 100. Again, venous side is 40. Gases are going to diffuse until they reach equilibrium, it's 100. Notice this didn't even drop it to 95 like the previous graph did. Keeps it very basic, which we should be right now, is getting the foundational stuff down. So it's carrying that PO2. The tissues that have much less oxygen, that need the oxygen to work, diffusion is going to occur until equilibrium is reached. On that venous side, oxygen, the body's extracted that 60 millimeters of mercury that it needed. What's left now is 40 on the venous side for oxygen. That goes back and the process starts all over again. On the CO2 side, if the CO2 in the alveolus is 40, and so that diffuses into the arterial system until there's equilibrium. That CO2 level is 40. There's more CO2 in the tissues. Again, so waste product of cellular metabolism. Reaches until there's equilibrium. So now we have a venous CO2 is around 46. That goes back into the lungs as it goes through the heart. CO2 levels higher in the venous system than it is in the alveolus. And the CO2 diffuses until what happens? Again, they reach equilibrium. I like these two pictures because it gives a very simplistic look at what that previous graph tried to do, but I think it's just my personal opinion, you guys may agree, it's just that first picture was just a lot of information altogether. But remember, maybe this could be confusing, but all of this is happening simultaneously. Now, maybe that other graph shows a better example of it. All that's occurring at the same time, the CO2 and O2 diffusing. But this kind of tries to take it out. You can see the numbers, and I've made sure the numbers are exactly still the same. So when I ask whatever question on the test, what's a normal this or what's a normal that, you know what those numbers are. I dropped it.
Oh, I broke it. I broke it. I can't have nice things.
Yeah, that's we're getting to that right now. All right, so what is the partial pressure of oxygen in the atmosphere? What is it in the atmosphere versus what is it in the airways? Partial pressure of oxygen. Again, and we're calling that 160, right? On the test, when I put the answer as 160, everybody's okay?
Yes.
Okay. All right. And I say, what about the airways? Remember, what are the airways? What do we have to add when we think about the airways? That 47, that moisture, water vapor pressure, which means the partial pressure of oxygen in the airways. And again, I'm calling that 150, right? 150 millimeters of mercury. That was from last week. I think it was last week. Week or week before.
Yeah, they all go together now.
Yeah, same here. Trust me, same here. Same here. Okay, everybody okay with these numbers? Because I know these numbers could be asked on the test as well. So you may think, holy cow, this next test, there's going to be lots of questions that deal with a very specific number, hard and fast number. Yes, there is. Yes, there is. Okay, so right now, in this room, that we know contains 21% oxygen, right? It's 21% of what? Barometric pressure at sea level 760. That's where that number comes from. If we say, okay, set 160 that's out here in this room, I breathe that in, that oxygen, not all 160 gets in my airways because I'm now humidifying, moisturizing, so water vapor pressure is going to take some of that spot. That's why I got to subtract water vapor pressure, 47, from the 760. That's 713. So 21% of 713 is that 150 number in our airways. Okay? We're getting to the alveolus. We're not there yet, but that's where we're heading next. So atmospheric oxygen is higher than airway oxygen because of the humidification. That water vapor pressure 47. Okay? Okay, that's rehashing what we talked about in the past. Airway oxygen, which we said was how much again? Approximately 150. Airway oxygen is higher than alveolar oxygen. If you remember that slide with all the graphs, what did we say alveolar oxygen was? About 100. Okay? So if the oxygen in my airways went from 160 to 150 in the airways, and now by the time it gets into my alveolus, it's 100. Well, what explains the difference? CO2 is now in the alveolus. So, so CO2 has to take up some residence, take up some space inside the alveolus. That's why even though our, again, oxygen out here, breathing room air is about, what do we say, 160. By the time it reaches my airway, because of moisture, humidification, it's about 150. By the time it reaches my alveolus, that oxygen number's 100. You know, why does it keep dropping? Because of carbon dioxide. Carbon dioxide. It is numbers, but it's carbon dioxide. And so, that gets me to this, what we're going to call and know as favorably the alveolar air equation.
No.
That's a moment of silence of for dramatic effect. All right, so to explain, and let me.
Moment of FMLR.
This is John's favorite formula of all time. Just to be clear, this is John's favorite formula ever on this planet, in this world, is the alveolar air equation. Okay. So, P, partial pressure, big A stands for alveolus, O2. So when I say, what's the P big A O2, I want to know how much oxygen is where? In the alveolus. The calculation, As you look at it, you may say, hey, I recognize some of that. Calculation is barometric pressure minus water vapor pressure times the FiO2. Okay, so times the FiO2. Notice there's brackets there, so you have to do that side first. That number is going to be subtracted from the CO2 divided by, what is R?
Respiratory exchange ratio.
Respiratory exchange ratio, which is 0.8. 0.8. Okay, so when I ask the test question, won't I have to tell you how much oxygen your patient is on? It could be room air, 21%, but it could be something different. I will have to tell you what I skipped this. The little a represents arterial. Arterial. So when we stick that blood gas, we draw from arterial blood. This is the CO2 of that arterial blood. So in a test question, I will have to give this to you. Now, barometric pressure, we're assuming at sea level, 760. What's normal water vapor pressure? 47. That number is not going to change unless we say our patient lives in Denver, Colorado, or some other location where there's a significantly different barometric pressure. But I will promise you right now, we're just talking about sea level. I'm not changing our elevation at all. Again, what's respiratory exchange ratio? 0.8. So when you do this calculation, you could take this last part and divide whatever their arterial CO2 is by 0.8. Okay, you can do that. What I do, and I'll explain why I do it this particular way. What I tend to do, instead of dividing that number by 0.8, I multiply it by 1.25. The number is going to be the exact same, so it honestly doesn't make a difference which way you prefer to do this. Either dividing the number by 0.8, that's a given, or multiplying it by 1.25. It really doesn't matter. But back in the day, up to 2 years ago, when the board exam then allowed a calculator to be used on their test, prior to that, students couldn't use a calculator. So this was the method we taught, because it's easier to take a number and multiply it by 1.25 than it would be to divide a number by 0.8. And so that's why so to this day, this is what I see when I solve alveolar air. It doesn't matter. It doesn't matter. And I don't want you to get confused. I say pick one or the other. Don't worry about trying to memorize both. The number's going to be the same. If you take someone's CO2 and multiply it by 1.25, or take their CO2 and divide it by 0.8, it's going to be the exact same number. Does not matter. But I do want you to understand, when I do it this way.
What is that number?
It's the respiratory exchange ratio, but where I now just multiply instead of dividing by the respiratory exchange ratio. Okay. Respiratory exchange ratio is what again? 0.8. It's not 1.25. But if I want to do this math to make the number be the same, I have to multiply by 1.25. So I say this is a constant. Just like the 0.8 I would say is a constant, this is a constant. Okay? I would have to give you this in a test question. I would have to give you this in a test question. I probably don't have to give you this part. You should remember it. And before, when we figured out oxygen in the airways, isn't this what we did? That part? Okay. What are we doing now? Because we're trying to figure out how much oxygen is in the alveolus. We have to figure out, well, how much space is carbon dioxide taking? That's why we subtract it. We have to figure out how much carbon dioxide is going to be in the alveolus, because I have to take that away from what this number is. Because remember, what did this number, this formula up to this point represent? The oxygen in the airways. All right? We're trying to figure out, because it's humidified, how much oxygen in the airways. The second half of this equation to figure out, okay, well, what part of the gas in the alveolus is going to be carbon dioxide?
Can I take a lifeline, please?
Phone a friend? Yeah, sure. So what does the alveolar air equation tell us? It tells us the partial pressure of oxygen in the alveolus, period. Wouldn't it be important to know, especially for your sick patient, gee, I wonder how much oxygen is in their alveolus, and I wish I could figure a way to know. this is how you know. This is how you know how much oxygen is available in your patient's alveolus. Does that mean all of that is getting into their bloodstream? No. Doesn't tell you how much is getting into the bloodstream. That's another day, another talk on another day, right? But it's a super easy one. It's a super easy one, I promise you. But this at least lets you know how much oxygen is available in your patient's alveolus. How much oxygen is available in your patient's alveolus. Again, we call it the alveolar air equation. So my question to you is, what's yours? How much oxygen is in your alveolus right now? Okay, so help me with this. What's barometric pressure? 760. What's minus water vapor pressure? 47. What's your FiO2 right now? 21%. Isn't that room air? So 760 minus 47 is 713 times 0.21, right? 21%. That's that side of the equation. Jot that number down, whatever it is. I know we might not know this. Maybe on those previous slides we did mention this. A normal arterial carbon dioxide level is about 40. It's about 40. So 40, if you like to do it my way, times 1.25. Or if you like to be different, and there's nothing wrong with being different, take 40, divide it by 0.8, your number's still going to be the same. So make sure for yourself that you can do the math. Because did standing on the chair emphasize how favorite of a formula this is? Yeah, I'm going to ask some formula questions from time to time. But if I am going to not omit one, which one am I not going to omit? I'll put this on every single test from here on out, and I don't care what class it is. It's that important, right? No, that's cardiopulmonary class. I don't care if it's patient assessment or neo-ped or whatever. You will learn it. You will like it. I mean, I don't like it, but you will learn it. You'll get sick of it, but you'll learn it. All right? So again, what is your alveolar air? It's about 100, right? It's about 100. You're welcome to take a picture of that if you want. Yes, I am rounding up and calling that 99.73 100. All right, 713 minus 760 minus 47 is 713. 713 times 0.21 is 149.73. On the right side, the CO2, arterial CO2, which is normally 40, times 1.25, or even if you divide 40 by 0.8, it's still going to equal 50. And then I'm going to subtract both sides from each other. What I'm left with is 99.73 millimeters of mercury. Obviously, I didn't round anything here. If you wanted to round, I think you're fine. If you call this 150, that obviously is 50, and then your answer is 100. You've already kind of did the rounding early. It's okay.
That's our baseline.
Right.
If you get sick, then we're gonna.
Of course, that's what it should be, right? That's what it should be for us right now. Now we know that sometimes patients get sick. No, that's a shocker. Sometimes their CO2 levels change, which obviously will change our number. We know that even though this is what oxygen is in the alveolus, because they're sick, ill, not all of their gases were easily diffused like they were supposed to, again, because of disease and illness. And I wonder why this patient's arterial oxygen level isn't the same as what's in the alveolus, because that's telling me what didn't get through. And that's why knowing this is so important, because when I do get their arterial O2, and I can see, man, that's really, really low. Well, how much was in the alveolus? Oh, it was 100. But only 50 got in, holy cow, there's something really wrong with this patient and their inability to get the oxygen from the alveolus into their bloodstream.
So, I'm probably going ahead a little too much, but when you start getting arterial blood gases, should the CO2 number be around 40 though?
Okay, yep, absolutely, absolutely. Okay, let's do a couple more examples. This is just us breathing room air, and everybody's okay with 21% is what the concentration of oxygen is in this room, right? Now I put our patient on 100% oxygen. They're very, very sick. Put them on 100% oxygen. Before you do the math here, wouldn't you expect, because you're giving them 100% oxygen now, wouldn't you expect the amount that gets into their alveolus should be much higher than it would be when they're just breathing 21%? Okay, should, but what should it be exactly? Now let's just assume their CO2 is still 40. Barometric pressure is still the same, water vapor pressure is still the same, so 760 minus 47 is 713. They're on 100% now. Is their FiO2 0.1? No. No, because 0.1 would represent 10%. They're on 100%, so this is going to be times 1. Be careful, that gets some people sometimes. And you know on the test, I'm going to make sure if they take 0.1, I'm going to make sure there's an answer. I'm going to make sure there's an answer there so you can get it wrong, but you're not going to get it wrong. Because remember, 100% is 1. What if their FiO2 was 99%? Then it would be 0.99. All right, CO2 we said will still be 40 times 1.25 or divided by 0.8, so that right side will still be 50. But what is this number?
63.
Well, but this side, so 760 minus 47 is 713. 713 times 1, so that side of the equation is 713. So 713 minus 50 comes out to be 663 millimeters of mercury. That's how much oxygen is where?
In the alveolus.
In their alveolus. Now let's say this is you. I'm expecting you to be healthy. When I draw your arterial blood gas and I measure how much oxygen is in your bloodstream, would you be satisfied if it was 100? Or should it be closer to 600? Again, I'm saying you're normal, you're healthy. If this is how much is in your alveolus, shouldn't that get into your bloodstream? Yes. So when you get a blood gas, and I'll tell you this, a blood gas P little AO2, arterial O2, normally is around 100, but that's breathing room air. You're breathing 100% oxygen, I expect it to be much higher, much higher. And again, if this is how much gets into your alveolus, and I'm saying it, again, I'm pointing to you, you're healthy, most of that should be able to get into your bloodstream. Again, why? Because you're healthy. If you had disease or illness, and I wonder, gee, why was their PO2 only 100 when they were on 100% oxygen? Boy, they really had something where the oxygen couldn't get out of the alveolus and get into the bloodstream. So that's a calculation we'll do later, but that's what alveolar air is helping me understand. When I know how much oxygen got into the bloodstream, that number needs to mean something to me. And I need to know, well, how much was in the alveolus, because then I can compare to how much got into the bloodstream. And again, if you are healthy, most of what's in the alveolus should be able to pass through the alveolar capillary membrane and get into your bloodstream. Question? We'll do this ad nauseum. I laugh. You know, coming in this morning, I knew this is what was in your day. When I'm talking about heat and humidity, I'm still thinking, oh, wait till they hear alveolar air. Their heads are going to start to spin or turn, kind of like they're doing right now. All right, so changing up the question a little bit. Still asking for alveolar air. Your patient is on a 40% Venturi mass with a CO2 of 30. What is their alveolar air, or what is their P, big A, O2? Again, what's the calculation? 760 minus 47 times what? their FiO2, which is 0.4 or 0.40 for 40%. That's the left side of the equation. That number will be subtracted from what? The CO2 times 1.25 or divided by 0.8. There's your second number. Subtract both sides from each other. That will let you know what is the alveolar air for someone on 40% with a CO2 of 30. Do this every year, guys. You guys are no different than any other class that's been through this for the first time. Wondering, what in the H is this alveolar air crap that he's bringing on us right now?
It ain't just H.
I was trying to be kind. I knew what you were in store for, yes.
That's why I was being all nice.
About 6-7 weeks, you guys know me like the back of your hand now, right? Now you're gonna be scared anytime I come in smiling. What if I come in and I'm not home? Today's gonna be a rough one, guys. Then you really know it's gonna be bad, don't you? All right, everybody get an opportunity to throw some numbers in there. I ultimately will have 2 questions on the screen with 2 answers. So if you want to save your storage on your phone, on your camera, wait till I get through the second one to take a picture. So answer here should be around 247, 248 if you round up, right? Okay, so and notice these numbers have not changed. They're going to be this. When it's time for a test, these numbers are going to be the same. The only time I will make this different is in the future when you guys are much more comfortable with this equation, and then I start changing barometric pressure on you just to you up, right? So that's going to be the same. FiO2 can vary depending on the O2 device, right? That could be all kinds of numbers, but depending on the O2 device, that's that side of the equation. CO2 obviously can vary depending on the patient. That number is always going to be a given, or divided by 0.8, always going to be a given. You have numbers on both sides, subtract them. So in this case, about 248 if I round that up. Everybody okay math-wise with this and the layout? Again, I know it's repetition. Second question. Now my patient's on a 28% nasal cannula, and they have a CO2 of 45. So what's their FiO2? 28, and their CO2 level right now is 45. What is their alveolar air? Calculation, everything's the same. You have a new FiO2, you have a new CO2 to deal with. John's favorite formula of all time.
Is that gonna be a question? What's John's favorite formula?
It might be. Could be a question that's on your national board exam. It could be a question on your national board exam, and you'll thank me, not now, but 2 years from now, and you're like, thank you for making me learn that, John, because they asked me that question. I'll go ahead and just say, you're welcome. All right, so same equation, 760 minus 47, which is 713, times our new FiO2, 0.28. That's the left side of the equation. Right side of the equation, CO2 is 45, so 45 times 1.25, or divided by 0.8, comes up to whatever it is. Subtract both sides from each other. Your answer should be, what did you get? 143. 143 and some change. Close enough. And if anybody wants to take a picture of it, you're more than welcome. That's everything on the slide, including the math. And I will say, as you're probably beginning to panic, it's this portion of this class where there's so much math. this portion of this class where there's so much math or calculations or formulas. The formulas, we're kind of reaching the peak where they'll start to level off.
I don't
Okay.
believe that.
Believe that? Did you see somebody's formula sheet? Sometimes second-year students will create formula sheets with everything listed. That looks daunting. That looks daunting, but it's like, yeah, it's 6-point font to fit everything on one single page. But really, this semester, we're kind of at the peak. It'll start to even off a little bit
Y'all heard
with
that?
math.
This
With
semester.
math. Of course, this semester, right?
This semester.
This semester. All right, everybody okay with the math, where the numbers are coming from, and obviously what I have to provide you in the question? Again, and I've said this with some other calculations we've done before. Right now, you have everything you need to solve this. However, in the real world, you're going to be given this, plus their heart rate, their respiratory rate, their blood pressure, their urine output, their breath sound, all this extraneous information that doesn't help me answer this question. So when I give you a question and I put some other numbers, you're like, wait a minute, I don't remember that number. Okay, maybe that's a distractor that I threw in there, trying to throw you off. You know you need the CO2, you know you need the FiO2. This is what I'm asking for, then don't worry about anything else. You don't need that information. All right, so I do have some questions. If you have some questions, you guys are more than welcome to snap some pictures here. First question is, at rest, what is normal CO2 production? Is it 44, 200, 250, or 1,000 mLs a minute?
44.
Right, those familiar numbers, right? You guys have enough knowledge now that there's so many numbers that are bouncing through your head for different topics that yes, I can throw those in as all wrong answers now just to mess you up. All right, so what's the answer here? Is it B or C? That should be the one we're torn between. Is it B or C? What is it? It is B. That means my follow-up question, normal oxygen consumption, then must be what? C. Okay? And I gave you both on here just so you can see it. When I asked that question verbatim, that you don't get them confused or mixed up. But like I said, I've had students before, I know it's one, and the other one's the other, but they just answered the same one for both, so they know at least they got it right one time. That means they also got it wrong one time. Get it right both times, and then you'll get maximum points. Again, you know what 44 is, and where I grabbed that number from something totally different. You know 1,000 is going to be a right answer for something else down the road, just so you know. For something similar, but different. Sorry. All right, next question. I think I have two more. What's a normal arterial oxygen level? Is that 100, 60, 46, or 40? Normal arterial oxygen level. Again, oxygen, arterial oxygen, which is on the graph, they're always what color? What's the blood color in that? Red, because it's carrying oxygen.
100.
It is 100. It is 100. Remember, and I heard you guys say it because you guys are so close to me. Alveolar oxygen is about 100, and it should diffuse until it reaches a equilibrium of 100 in the arterial system. Okay, in the arterial system. Now, let me look at my. I want to make sure I'm asking the same question later. Okay, I'm not. So, if this is what the oxygen concentration is in the arterial system, and that's what ultimately it takes to the tissue, and the tissue takes the oxygen it needs, what's left over? That's the 40 number, oxygen-wise. Remember, there was a difference of 60 as far as how much the body takes from oxygen? Another question, this is my last question. What is the normal Venus CO2 level? Venus CO2. Is it 100, is it 60, is it 46, is it 40? You're at 46? It is 46. 46 is correct. On the arterial side, to change up the question, on the arterial side, CO2 is about 40. Venus side 46, remember? Difference in CO2 was about 6, where the difference in O2 was about 60. Okay? Questions? Why are you packing up? You know what's coming next?
No.
Okay? Thought you would prepare me by now. I thought we were together on that. Look what I have. Oh, goody. Goody. I can drop my favorite formula of all time and not give you a word.
No one was
But I won't. I said I'd let you get out of here early, and I am letting you get out of here early. You're welcome. But as soon as we finish this, there's only 4 questions. Only. Famous last word. Only 4 questions. You're welcome. Just when I thought you guys knew me, already leaving.